Hello, my name is Gideon Mpungu, and welcome to my presentation of the paper predicting solar radiation using artificial neural networks. And we're doing a deep dive in different backpropagation algorithms. This particular study focuses on solar radiation, which we know is an alternative to fuels, to fossil fuels that cause a lot of adverse effects in the environment. In this study, we will look at employing artificial neural networks and backpropagation algorithms to be able to achieve this. For this study, the methodology that is used by the researchers is as shown in our slide. The obtained data is first of all processed accordingly to prepare for the AN model training. Based on this data, optimum neurons are then selected, which provides better training accuracy. The processed data and the selected optimum neurons are then used to train the intended models. Best models are selected using statistical analysis and then compared with different models developed in literature. So that is the methodology that we're using for this particular paper. To go a bit more into the multilayer perceptron and neural network architecture, let's begin by exploring this architecture in our slide. The researchers, as we'll see later, developed 4 artificial neural network models, each with different combinations of meteorological inputs, so variations of temperature, relative humidity and speed, different pairs of those. And the architecture of these networks consisted of one input layer, one hidden layer which had 15 nodes, and one output layer which predicts the global solar radiation. This structure highlights the significance of choosing the right combination of input parameters to improve prediction accuracy, and we will expand a bit more on this slide later. From this particular slide, we see how MATLAB is used to train the network using the input data through a series of transfer and activation functions, and subsequently being able to predict the output with minimum error. As we can see from this figure, the architecture of an artificial neural network is made up of a series of individual components, which are in fact represented in matrix form. From the network can be used as a general function approximator to approximate any function with a finite number of discontinuities. The accuracy of approximation depends on the number of neurons in the hidden layer, and a few key parameters to take note in the architecture that we can see there is that, as you can see, N1 represents the number of neurons in the input layer, while M, if you're paying attention to our input layer, while M represents the number of elements in the input layer. The input weight matrix IW, as you can see, is our N is calculated as N1 times M, whereas B1, which is our bias vector, and we'll touch more about bias in a later slide, is N1 length matrix. This is similar for the components in the output layer, as you can see, and only differentiated by the superscript 1 and 2 beside the matrix, where 1 would mean that the matrix is associated with the input layer and 2 means that the matrix is associated with the output layer. A1 is a transformed matrix from the hidden layer that has undergone transformation through the tan-sig, or what we usually call the tan-sigmoid function. The tan-sig transfer function is a function that takes a matrix of net input vectors S1 and returns a matrix A1 in the range between -1 and 1. Similarly, A2 is a transformed matrix from the pure line, or what we usually call a linear function. Pure line transfer function works similarly as the tan-sig function, except for that it takes the input to transform it and return it linearly in the range -1 to 1 again. Hence, the AN model will be trained with 3 different backpropagation algorithms, as we'll see, LM, SCG, and BR, to reduce the error rate and make a more reliable model with increasing its generalization. Especially for this model, as you will see, our input layer is made up of meteorological data, that is the temperature, humidity, and wind speed, and our hidden layer is made up of 15 nodes. As we will see, there's a reason why we selected these 15 particular nodes, and the output layer is made up of our actual solar radiation prediction. In this next slide, we see how we actually determine. As we talked about, we chose 15 nodes for our hidden layer. In this slide, we see how this is actually determined. Determining the optimum number of hidden neurons, right, or nodes, or hidden nodes in the hidden layer can be a very complicated process, as you can know from your background of deep learning. Having the optimum number of hidden neurons is able to ensure a greater accuracy of our artificial neural network model and achieve a minimum possible error in the output. In order to select the optimum number of hidden neurons in the hidden layer, a model 4 was developed by increasing the number of neurons one by one, as you can see, until it converged into the smallest mean squared error. Since our model, the Levenberg-Marquardt or LM algorithm, is one that produces the highest R value in the range of 0.7 to 0.8, as you can see, among the 4 algorithms, the LM algorithm is used in the selection of the optimum number of hidden neurons. As shown in our table there, the model 4 is trained several times using different number of hidden neurons, and the R values for both the training and testing is slowly increasing as the number of neurons is increased. When the hidden number is increased until 15, a maximum R value for both the training and testing data is reached, which is 0.8, 0.24 for training, and 0.8231 for testing. This means that the predicted values show great correlation with the actual values and they are consistent with each other. So this is why we actually choose the 15 neurons, because when we actually, as you can see in our table, when you try to increase them to 20, when we start increasing our neurons past 15, then the value of R actually starts decreasing. So we choose 15 as our optimum number of neurons or optimum number of hidden nodes in our hidden layer. So now we're going to look at how our artificial neural networks are actually built, right? Like we said, we're already splitting it into 4 models based on the different outputs. For model 1, we're taking the mean temperature, 24-hour mean temperature in degrees Celsius, and the mean relative humidity in percentage. Model 2, we then look at the mean temperature and the mean wind speed in meters per second. Model 3, we then take the relative humidity with the mean wind speed. And as we already hinted on, for model 4, we are going to take all our meteorological inputs, right? So all our 4 models have one output, which is the global solar radiation, and we can go back and apply this to our architecture as we saw, and it actually fits in properly. Among the 4 models, the best artificial neural network model with the backpropagation algorithm, which exhibits the best predictive ability, is selected based on the minimum mean absolute error, or MAE, minimum root square error, RMSE, and maximum linear correlation coefficient, which formulas of these I think can be easily found online. Okay, next we look at activation functions and backpropagation algorithms. Um, the study employed the 3 backpropagation algorithms: Levenberg-Marquardt, scaled conjugate gradient, and Bayesian regularization. These algorithms were chosen to reduce error rates and enhance the model's reliability and generalization capabilities. The key findings was that the Bayesian regularization, or BR algorithm, trained AN models exhibited maximum performance with a high correlation coefficient and minimum root mean square error, outperforming models trained with the other models. In terms of learning paradigms, the study predominantly used supervised learning. The AN models were trained with historical meteorological data to predict solar radiation, and this approach is crucial as it involves training the model with input-output pairs, allowing the ANN to learn and make predictions based on new unseen data. Based on our results there, it can be seen that the BR and LM trained in ANN model are far more superior to the SCG trained model in terms of predictive ability and accuracy. And this is probably due to the fact that SCG uses less memory in training the data as well as faster training time. However, in comparing the BR and LM algorithm, BR algorithm still has a slight edge compared to LM algorithms, as its key statistics are pretty close. This is due to the various advantages of BR algorithm, such as its robustness of the model, probability distribution of the network weights approach, and optimization of the ANN architecture. This will help us in overcoming overfitting issues due to the better data generalization ability. Hence, it can be said that the Bayesian regularization of BP algorithm is the best suited algorithm in our study to develop solar radiation predicting artificial neural network model. As we can see in our critical analysis using the MAPE for each model, the study still emphasizes, the paper still uses an approach for error correction that emphasizes the effectiveness of the Bayesian visualization algorithm in minimizing prediction error and optimizing the model. Now, in conclusion, this study presents a significant advancement in using artificial neural networks for solar radiation prediction, especially highlighting the importance of selecting appropriate backpropagation algorithms and input parameters. Thank you for listening.